Today, we're going to peel back the layers of the chemical bond to uncover this hidden world of pushes and pulls and, well, three-dimensional geometry. We are going to map out the vector blueprint that basically dictates how molecules behave. And you know what? What we find might just change the way you see everything on a molecular level. So let's dive right in. Okay, first things first. We need to throw out a pretty common idea you probably picked up in chemistry class. We often learn about two totally separate types of bonds. You've got covalent, where electrons are shared, and ionic, where one atom just steals them from another. But the truth? It's really more of a spectrum. No bond is ever 100% one or the other. It's all just a sliding scale of sharing. And this simple idea, well, it's the key to everything else we're about to unpack.
So, if bonding is a spectrum, how do we figure out where a specific bond falls on that scale? Well, we start by looking for something called the vector of polarity, which is really just the specific direction that the electrons are being pulled. And this slide shows the two scenarios perfectly. So over on the left, you see a nonpolar bond between two hydrogen atoms. Think of it like a perfectly balanced tug of war for electrons. Nobody wins. But on the right, with hydrogen fluoride, we've got a totally different story. Fluorine is what we call highly electronegative. It's like it has this super strong magnetic pull for electrons, so it yanks those shared electrons much, much closer to itself. This creates that directional shift, a separation of charge, which is what makes the bond polar. And that little crossed arrow you see, that's our very first vector, pointing from the slightly positive end over to the more negative end.
Now, to measure the strength and the direction of this pull, chemists use a concept called the dipole moment. It's represented by that Greek letter mu. You can just think of it as a precise numerical value for how polar a molecule is. It's the tool that turns this kind of abstract idea of electron pulling into hard, solid data. The formula itself is actually pretty simple. The dipole moment, mu, equals the magnitude of the separated charge, which we call Q, multiplied by the distance between those charges, R. So the charge magnitude and the distance, they're like two inputs that determine the final reading on our dipole moment meter. And the result is expressed in a special unit called the Debye, or just D. All you really need to know is that a bigger Debye value means a more polar bond. Simple as that.
But this is where it gets really cool. A molecule is way more than just one bond, right? It's a three-dimensional object where all these different bond vectors can interact. They can add together, or they can even cancel each other out entirely. The water molecule is the perfect example of this idea of vector addition. So each hydrogen-oxygen bond is polar, and its vector points toward the oxygen atom. But because of water's bent shape, these two vectors don't just cancel out, nope. Instead, they combine to create a single really strong resultant vector that points straight up. This gives water a pretty significant net dipole moment of 1.85 dBi, which, by the way, is responsible for a lot of its unique properties, like why it's such a great solvent.
Now let's look at the complete opposite case. In beryllium difluoride, which is a straight line, the two fluorine atoms are pulling with the exact same force in perfectly opposite directions. It's a molecular stalemate. The individual bond dipoles are super strong, but they completely cancel each other out, giving us a net dipole moment of 0. And the same thing happens in boron trifluoride. The three fluorines are pulling outwards at perfect 120-degree angles, and again, their vector sum is 0. This is a huge takeaway. Perfect symmetry can literally erase a molecule's polarity. Okay, so we've got our rules down. Electronegativity creates polar bonds, and the 3D geometry decides if those polarities team up or cancel out. But now, let's investigate a case that seems to just break all the rules. So here's the mystery. We know fluorine is the undisputed champion of electronegativity. It pulls on electrons harder than any other element. So logically, if we take ammonia and swap its hydrogen atoms for fluorine atoms, we should get a much more polar molecule, right? A way bigger dipole moment. Well, let's see what the evidence says. And the data is, well, it's shocking. On the left, we have ammonia, NH3, with a pretty respectable dipole moment of 1.47 dBi. But on the right, nitrogen trifluoride, NF3, has this tiny dipole moment of just 0.23 dBi. It's almost nothing. Replacing hydrogen with the powerhouse fluorine somehow almost completely destroyed the molecule's polarity. What on earth is going on here? The solution to this whole paradox lies in mapping all of the vectors. Turns out we've been missing one absolutely crucial player in our analysis this whole time. And here it is. This is the big reveal. Let's do a little vector autopsy.
The missing piece is the lone pair, that unbonded pair of electrons just sitting on top of the nitrogen atom. It creates its own powerful upward-pointing vector. Now, in ammonia, nitrogen is more electronegative than hydrogen, so the 3 bond vectors also point up towards the nitrogen. All 4 vectors are working together, they're synergetic, creating a big dipole moment. But in nitrogen trifluoride, fluorine is more electronegative than nitrogen, so those 3 bond vectors now point down, away from the nitrogen. The lone pair's vector still points up. They're now fighting each other, they're antagonistic vectors, and they almost completely cancel out. Mystery solved.
And so we reach our final verdict. When it comes to molecules, it all comes down to one thing. Geometry is destiny. The 3-dimensional arrangement of atoms and electrons is the ultimate decider of how a molecule is going to behave. This grid just sums it all up beautifully. Look along the bottom axis, the symmetry zone. This is where you find molecules like CO2, BF3, and CCl4. Even though they have very polar bonds, their perfect linear or trigonal planar or tetrahedral shapes make sure that all the vectors cancel out, giving them a dipole moment of 0. But as you move up into asymmetrical shapes, like bent water or trigonal pyramidal ammonia, their vectors add up and boom, they become polar. So the ultimate takeaway from all of this is pretty simple. Molecular polarity is never just about what atoms are involved. It is a dynamic, 3-dimensional negotiation between electronegativity, lone pair orbitals, and spatial geometry. To truly understand why a molecule acts the way it does, you can't just count its charges. You have to map its vectors.